Okay, so first of all, there's the idea of oxidation number. All right, this is how we keep track of either the real or the imaginary charge on something. All right, so it's called oxidation number. Real or imaginary charge. So for instance, what's the charge on a piece of aluminum? On this aluminum chalk tray, what's its charge?
Neutral there.
Neutral. It has no charge. I didn't grab a hold of it and go, ah, and get electrocuted, did I?
Well,
No. All right, and so it has a 0 oxidation number. Any element has a 0 oxidation number. All right, now, Gesundheit. Now, next one, ions. If it's already a charged ion, its oxidation number is its charge. All right, so if it's a charged ion, an ion is a charged atom, the oxidation number is simply the charge. So this is a +3. All right, now notice the difference. You'll notice we've been talking about charges. We've been writing them. There's a convention that says you write charges as 3+, and when we write oxidation numbers, we write them as -3, +3, whatever it is. Okay, should be easy to remember. All right, now we get into the weird bits. All right. If it's ionically bonded, then it's easy to tell because, again, we just go with the charge. However, if we have something that is covalently bonded, they still can have an oxidation number. All right? Example being, let's start with a simple one, water. All right? There are two elements in water, hydrogen and oxygen. Oxygen's oxidation number is almost always -2. Hydrogen's oxidation number is almost always +1, but not always, just mostly. All right? Everything else, we kind of have to determine how many electrons it's sort of kind of holding on to. So what does this idea mean? In this case, aluminum has exactly the number of electrons it's supposed to. It's neutral. So it has no oxidation number, no charge. In this case, aluminum has lost its 3 electrons, so it has a +3 charge, so it is a +3 oxidation. Now, if, for instance, we go back to what we saw in the lab, if we take nitrate ion and we have nitrogen dioxide, that is a redox. All right? Going from one of these to the others of those is redox. All right? So what did it do exactly? Here's how you determine the oxidation number. You're going to take the compound. Let's start with nitrate. Nitrate, NO2. What did we say just a moment ago? What's typically the charge or the oxidation number of oxygen? -2. How many oxygens are there?
2.
2 of them. So each of them contributes a -2. Total of -4. If this thing is neutral, it has no charge, it's that brown gas you saw, it had no charge, then the charge, real or imagined, on the nitrogen has to be the same as the charges from the oxygen. The oxidation numbers of the oxygens plus the oxidation number of the nitrogen have to add up to 0. What, therefore, is the oxidation number on the nitrogen?
+4.
+4. Does that make sense? Okay. Let's try the other one. Let's try the nitrate. Okay. What's the... We good? Okay. What's the oxidation number on oxygen again? -2. There are 3 of them. So it's -6. Now notice, this thing has a charge, so when we're done, it has to end up -1. Does everybody see that?
Yes.
Ergo, hence, thus, therefore, what's the charge or the oxidation number on the nitrogen? +5. All right? So, what we're saying is that this reaction is redox. We're saying that this was a +5 oxidation number on this, Now it's a +4 oxidation number on the nitrogen.
Oh, so it can change?
So, yeah, it's physically changing what's called oxidation number. Now, it's not the real charge. These are covalently bonded, and they're pretty close, try again. They're pretty close to perfectly covalently bonded. They're only slightly polar. So it's not like the nitrogen really is missing 5 electrons and the oxygens really have 6 extra electrons between the 3 of them. It just means that this is kind of a bookkeeping system we use to say where have the electrons sort of kind of move from one place to another.
So the redox for NO3 minus to NO2 is the nitrogen?
The nitrogen is the element that has been reduced or oxidized.
Okay.
Okay? So there's a compound that's changed. We've changed compounds from one to another. This was a colorless ionic solution, and this was that funky brown gas that you saw, right? So this has changed its redox number, its oxidation number from +5 to +4. Now, yes, sir.
How do you do, if the covalent bond doesn't have an oxygen or a hydrogen, how would you do it? Like find out oxygen.
Now that would be a little tougher, okay? I don't know that you have to worry about that over much because most of the time it's gonna be anything that's ionically bonded, we're gonna have oxygen or hydrogen in it.
Oh,
So we should be okay. Now I can make a more complicated molecule, but it's still, you'd be able to work out what the oxidation number is. Question?
So when you have the O2 and the O3, are you dealing with oxygen molecules versus oxygen atoms?
No. Good question. The idea is the nitrate or the nitrogen dioxide just means you have 2 oxygens connected to a nitrogen, and overall the molecule has no charge. Up here, you've got 3 oxygens connected to the nitrogen, and overall, the molecule, Mickey, get out of there. Overall, the charge is -1. So the whole molecule, or ion, has a charge. But it's not oxygen. O2, just because it says O2, doesn't mean that that's oxygen gas. Because you know that because you tried to breathe that brown stuff in, it definitely won't breathe well. All right? Does that sort of kind of make sense?